Thank you for that, Professor. But yeah, as Xuanglun said, my name is Ryan. I am a grad student at the University of Kansas, and I am a fifth year. And I'm going to be presenting some work that Xuanglun and I did together. The topic is extremisers to the Strichartz Inequality in Dimension 1. So here's the outline of everything. We're going to go through the basics. We'll talk about the basic ideas that are needed to discuss this. I'll go through the history of the problem, who's done what, who's studied it. I'll give the main idea that we want to show. There's two main ideas that we want to show. I will develop the extremizer to Strichartz inequality. I'll give some properties of these extremal functions. And then using those properties of the extremal functions, I'm going to show that extremal functions are actually L2 functions. And then we'll have time for some questions afterwards. All right, so the basics are, we have this operator, e to the IT delta f. We take the Strichartz inequality, takes the L2 plus 4 over D norm of that, where D is the dimension of our spatial variable. And that's bounded above by some constant, which depends on our spatial, or depends on our dimension, times the L2 norm of f, where the LP norm is your standard LP norm. And this operator here, e to the IT delta f, is 1 over 2 pi integral of e to the I x dot c plus I c squared t times f hat, where f hat is the same Fourier transform that everyone knows and loves and uses every day. And x is a spatial variable. And we have a similar definition for our space-time Fourier transform. All right, so that's the basics that you need to know. We're particularly looking at the case dimension D equals 1. So that makes our Strichartz inequality e to the IT delta f, where we take the L6 norm of it, and it's bounded above by some constant times the L2 norm of f. And we have this sharp constant where it's just the soup of this quotient here. And the maximizers are what give equation 1 that inequality and make it an equality for that sharp constant. And they have this form of a Gaussian. Now, it's been shown before that it's a Gaussian by Damiano-Fossky, or Fosky, one of those two. But so the history of this, so Strichartz in 1977 showed that e to the IT delta f is a solution to the Schrodinger's equation, where f is your initial condition. Kuntz showed that extremisers do exist for dimension D equals 1. Xuanglun Xiao showed the existence of a maximizer in all dimensions for non-endpoint Strichartz inequalities for the Schrodinger equation. Damiano-Fossky showed that they have this Gaussian shape. Now we're also going to show that they have this Gaussian shape, but we're going to provide, an alternative proof of this. Hundert, Mark, and Zarnitsky found a new representation, and they used an orthogonal projection operator to do this, specifically in dimension D equals 1 and 2.
So, Ryan,
yes.
Can you classify the non-endpoint means?
Non-endpoint?
Yeah.
Yeah, so, and are you saying in this paper here?
Yeah.
Yeah,
I forgot my results. Yeah. So.
Yeah. So the existence of the maximizers for non-endpoint Strichartz, so there should be a p-value that this holds for, and it doesn't include the endpoint of that p-value, if I understand correct.
Okay.
Yeah, so, Brochi, Silva, and Quilo-Dran, they showed sharp Strichartz inequality for fractional and higher order Schrodinger's equation. Specifically, they showed that it enjoys a rapid L2 decay for extremisers. Now, this is something that we're going to take advantage of during the proof. We'll give a very, very brief description of the proof for the decay. All right, so we have two main goals that we want to show. First, we want to show that extremisers are Gaussian. Now, again, remember, Fossky showed that they were Gaussian, but we're going to give an alternative proof to Fosky's proof. Likewise, we want to show that if f solves the generalized Euler-Lagrange equation, then that implies that e to the mu c squared f hat is an L2 function for some mu. And we'll find the specific mu that works for our case. All right, so those are our two main goals. And in fact, once we show this, that's going to imply that f is real analytic. So for now, just suppose that it's real analytic. We'll show that in a moment, but for now, just let's assume that it is. Foskey showed that we have for an extremizer f in a corresponding, remember, this is the spatial one, and this is the space-time function. He showed that it enjoys this this equality here. Fx, Fy, Fz is equal to x squared plus y squared plus z squared, x plus y plus z. All right, and we're going to use this to show that they are in fact Gaussians. So if f is a maximizer for Strichartz inequality, then, like I said, it is a Gaussian. So here's the idea of the proof. So for 2 points in R3, if it satisfies this, a plus b plus c is equal to d plus e plus g, and the sum of the squares is equal to the sum of the squares, then we get that f of a, f of b, f of c is equal to f of d, f of e, f of g. Now, something to mention here, using this equality, Damiano Foskey showed that extremizers, or anything that actually satisfies this equation, is if it's zero anywhere, then it's zero everywhere. So we're assuming that this is a non-trivial solution, so we can assume that it's non-zero anywhere. That being said, that means we can take the natural log of this. And we're going to look at this, we're going to call it phi. The natural log is going to be phi. Then we're going to take the expansion of this. And
Right?
yes.
How do you say that's a positive function?
This?
Yeah.
So yeah, Foskey showed that it should be in his paper, his 2006 paper, I think.
It shows you never have zero, right? So, but it might be positive sometimes, it might be negative sometimes.
Weren't we assuming it was real analytic though? So
Yeah.
it should be continuous.
Right.
Okay. Yeah. Okay. Good.
Yeah, if it's real analytic, it should be fine, right?
Okay. Good.
But yeah, so we take the Maclaurin expansion of this, and because of this here, this equation 2, or I guess set of equations here, it turns out everything drops out, and it leaves phi to be just a quadratic, which of course means that f has to be a Gaussian. All right, so let's talk about some properties of the extremal functions. We're going to consider this Q, and it seems out of place now, but you'll see why it's important in a moment. Takes inputs f1 through f6. We take the Fourier transform of everything. We take the Fourier transform of everything, and we've got our deltas here, where we've got a k c and b k c, where a k c and b k c are expressed this way. And this I'll mention in a moment, but this is equal to an integral of e, in the distribution sense. So yeah, down here, integral of e to the I k c x in the distribution sense. Now, if f is an extremal function to Strichartz inequality, then it must satisfy the Euler-Lagrange equation, which is for all L2 functions g, we have an omega such that the inner product of the two is equal to q g f f f f f, where omega is defined down here. And we're gonna take advantage of this here in a moment. So when a k-c satisfies this R6, then we're going to satisfy, we can break it up into 2 parts. That works for equation 2 as well. So we're going to define this function. This is probably bad notation, but this k-c is an R1. This is an R6. I probably should have chosen a different variable, but we're going to define this way. And, you know, it should be easy. You know, some Calc 1 shows that this is an an increasing function. You just take the derivative of it and everything works out really well. Using this, and for some functions that are L2 functions, we're going to define the weighted multilinear integral to be the integral of e to this difference here, where it takes the first one and then subtracts off everything else, times the product of all these. Now, again, since this is increasing, it can be shown pretty quickly that this is less than 0. Since that's less than 0, that means that this weighted multilinear integral is bounded above by the integral of these products with these deltas attached on to the end. Furthermore, this is a result from Brochi, Silva, and Quilla-Dran. This estimate right here, the bilinear, enjoys this exponential decay when the support of H1 is bounded between negative s and s, and the support of H2 is bounded outside of ns for n and s very large. Again, these are R1 functions, so this is an R1, not the R6 one that we were discussing earlier. The same thing here. This is, again, I should have used different variables for this. So hopefully that's not confusing. So if we pair that, if we pair this with the L6 to L2 Strichartz inequality with some holders, we get that this multilinear form, this multilinear weighted integral, is bounded above by n to the minus 1/6 times the product of our HKs. All right, so why is that important? Well, let's talk about this here. If I have f that solves the generalized Euler-Lagrange equation for that omega, and I normalize my f, normalize the L2 of my f, I'm going to define f hat to be restricted to being greater than s squared for some large f, or sorry, large s. Then for mu, such that s is, or mu is equal to s to the minus 4, I have this polynomial bound above this term here. Now, something that's important to note is that this term goes to 0 uniformly, as does this term, and all of my other constants independent of epsilon and s. All right. So here's the outline of the proof. This follows the two-dimensional proof pretty closely. But basically what we do is we write this out as an inner product, we move stuff over, and we end up getting this representation down here. Now, since f satisfies equation 6, we have this q right here. Well, I'm going to define h in a nice way where it's just EF C1, F hat C1, H greater than, and the way that you would expect, F hat less than the way you would expect, and same thing with H less than. So now what I'm going to do is we're going to say that this is now, once we replace everything in, is actually just equal to this weighted multilinear integral here. So what I'm going to do is I'm going to break this up into different parts based on the last 5 terms of this. So I've got the first one is all H less than for each one of the last ones. And I got my B1, B2, B3, B4, B5, where BI, each one of these is either going to be less or greater than or less than, but exactly I of these is going to be greater than. So specifically, for an example, B1, out of the last 5, one of them is going to be greater than. So here's the first one, here's the second one, here's the third one, here's the fourth one, here's the 5th one, right? And it's going to be the exact same way for all the other B2, B3, B4, B5. All right, so now what I can do is this first term, this is the very first term, I can bound this using that operator, or that bound that I had earlier, using the result from Brochi, Silva, and Quilla-Dran, to bound this above by a constant that depends on s, times h greater than. And doing the exact same thing, I can bound bk by h greater than k to the plus 1. Specifically, when k is equal to 1, this constant is going to depend only on s. All right. Well, that means this is going to be bounded above by this polynomial, this 6th degree polynomial, essentially polynomial. Now, if I divide out by one of these terms, I get the desired result. All right. So now what I need to do is I need to show that this, given that above result, I need to show that it is now an L2 function for some mu. Turns out mu is going to be s to the minus 4, as we saw in the above result. All right, so here's the outline of the proof. I'm going to define this function to be h of epsilon, where it depends on this epsilon, and s is a large fixed constant that we can control. So think of it kind of like a delta in a continuity argument. You know, we can control that delta in a continuity argument.
So, Ryan,
Yes.
the actual, I mean, when you say the high-low bounds, I mean, on your previous page,
This one?
yeah, so you say you're using the that 3 results, right? Actually, you should trace back to my earlier paper with Hundermark.
Right, that
Yeah.
it's this paper. That's what this is.
Yeah, that's where we first use the high-low, so the interaction between high-low waves is weak. So that's where I think that's also Jembergen's idea. Okay, so you should mention Jembergen.
Oh,
So you
okay,
didn't
yeah.
mention Jembergen, you mentioned that paper. So that's their paper deal with this estimate, but it's not necessary saying that that's their work. That's wrong. Yeah.
Okay, I thought it came from, I found it in this paper, so I didn't realize it. I thought it came from here. I didn't realize it went back to that one. So I'll make sure to make that edit.
Yeah.
Yeah, so let's see. Yeah, so we have this function here. Again, this is basically our delta in our continuity argument. It's a large fixed constant that we can control. Let's see. Oh yeah, it's continuous. We can show that it has to live inside an interval. If we go back to the previous lemma, that means it must be bounded. So by monotone convergence, this is going to be an L2 function. Yeah, so then by dominant convergence, I use the Fourier inverse, take the derivative with respect to z bar, ends up being 0, and so it's entire. All right, so yeah, we said we wanted to show that it was Gaussian and that it was analytic, and we said, well, assuming that it's analytic, turns out it's going to be Gaussian, and then we show that it is in fact analytic. So, all right, any questions?